This is a video about Hess's law. I am going to go over two problems with you. One is what I consider the longhand version, the long way, which is where I give you the sub-equations and you have to rearrange them to figure out the delta H of an overall reaction. And the other one is where I do not give you the sub-equations. You have to find them in the reference packet, but there is a shortcut for that method. I'm going to do the long one first. So in this one, this is the overall equation that we want to get to. 1 mole of methane reacts with 1 mole of ammonia gas to produce 3 moles of hydrogen gas and 1 mole of HCN, hydrogen cyanide. Now, these are the 3 sub-equations that we have to work with. We have to make sure these are orientated the correct way to give us this overall equation, because what we want to do is figure out what the delta H is going to be for that equation. So when I'm working on these, what I like to do is start with the first reactant. And what you want to do is find this reactant in the sub-equations. It only shows up once right here. And there's 2 things you want to look at. For one thing, you want to make sure it's on the correct side of the equation. We want the methane to be a reactant. And here it's drawn as a product, so we're going to have to fix that. The other thing we're looking for is the coefficients have to match. This is like having a coefficient of 1 in the overall reaction, and in the sub-equation it has a coefficient of 1, so that's good. So the only thing we have to do is flip this because we want it as a reactant, but it's shown as a product. So I'm going to make a note of that. I'm going to write flip, and remember, whatever we do to the chemical equation, we have to do to the heat term also. So I'm going to rewrite that equation flipped. So now the methane, the 1 mole of methane that was a product, is now the reactant. And we have solid carbon and 2 moles of hydrogen gas. I'm leaving out the abbreviations like gas and solid just so it's a little less cluttered when I'm writing it out. So now that we have that 1 mole of methane figured out, we're going to move to the next thing. 1 mole of ammonia gas. We look for it. It only shows up in one spot, which is right here. Now again, 2 things you have to look for. You want to make sure it's on the correct side of the equation. It is a reactant in the overall equation, but it's a product in the sub-equation, so we have to flip that equation. And the other thing that is not matching up is we want 1 mole of ammonia gas, but here it's shown as 2. So we have to get this equation down to 1 mole of ammonia gas, and that means we have to divide by 2. If you divide one thing by 2, you have to keep the ratios all the same, so everything gets divided by 2. So now I'm going to rewrite that equation, flipped and divided by 2. So now the 2 moles of ammonia that were products now are 1 mole of ammonia that is the reactant. The N2 gas becomes 1/2 mole of N2 gas. And 3 moles of hydrogen gas, I'm going to write as a decimal, becomes 1.5 moles of hydrogen gas. If you wanted to, you could write it as 3/2. It means the same thing. It doesn't really matter. Now, the delta H, and I just realized I forgot the delta H for the top sub-equation, so I'll have to go back and do that. Delta H for this one, it starts off as negative 91.8, but we flipped it, so that's going to make it positive. And when you take 91.8 divided by 2, you get 45.9 kilojoules. The first sub-equation, I forgot to fix that one. That is the one with methane. All we did was flip it, so it becomes 74.9 kilojoules. Alright, so that takes care of 2 of the sub-equations. We have to figure out what to do with the last one. The next thing in line is 3 moles of hydrogen gas, but it shows up in each of these sub-equations. And really what happens, a lot of times when it shows up in more than one sub-equation, I just tend to skip it, just because a lot of times you're not sure what to do with which equation, and that 3 moles of hydrogen gas will work itself out in the end. So I'm going to skip that because it shows up everywhere. And the last thing is 1 mole of HCN, that is a product, and here it is here. It's shown on the product side, so we do not have to flip it, but the coefficients don't match. This has a coefficient of 1, here it's shown with a coefficient of 2, So for this sub-equation, we are going to divide by 2. So that 1 mole of hydrogen gas becomes a half mole of hydrogen gas. The 2 moles of solid carbon become 1 mole. Oh, I forgot about the nitrogen. Sorry. The 1 mole of nitrogen gas becomes a half mole of nitrogen gas. And 2 moles of HCN become 1 mole of HCN. Now, since I divided the chemical reaction by 2, I have to take the heat term and divide it by 2, and that positive 270.3 kilojoules becomes 135.15 kilojoules. Now, what we want to do is double check our work at the end here to make sure we have this all set up right. And the way you do this, if you have any repeats on the same side of the arrow, they would get added up. Anything that shows up on one side and in the other would get consumed. It's basically like saying in one sub-equation something gets made, but then another sub-equation it just gets used up. So solid carbon, for example, it's being created by this sub-equation but consumed by that one. So that would cancel out. You would end up not seeing that at all. The half mole of nitrogen gas is a product here and a reactant here. So that gets consumed. Now I have 2.5 moles of hydrogen gas on the product side and a half of a mole on the reactant side. So what happens is this 1/2 is going to go away. And really what that does is that takes care of that 1.5. It takes half of that away. So I end up with a net gain of 3 hydrogens on the product side because it went from 3.5 on the right to subtracting out this half on the left. Now I canceled out everything I could, so I'm going to write down everything that's left over. I have the 1 mole of CH4 on the reactant side, the 1 mole of NH3 on the reactant side. I have the 3 moles of H2 that were left there, and I have the 1 mole of HCN. Now when I look at this reaction should end up matching the overall reaction. And it does, so that means I did it right. Right? That's how we double check our work. Now, the only thing that's left is adding up all the delta H's. So you're going to do a positive 74.9 added to a positive 45.9 and then added to a positive 135.15 kilojoules. What you end up getting is 256.0 kilojoules. I'll put a positive there just to emphasize it, although technically you don't need the positive. So before even doing that reaction, you should expect to have a positive change in enthalpy, 256 kilojoules as to delta H. Now that was the long way of doing this one, and I'm going to show you the shortcut that we could do for the other problem. So what happens here, the next problem is this one. And what you have to do is make a note of the 3 things that are in this problem. So, well, not 3 things, the 4 things. The NH3, the O2, the NO, and the H2O. Now pay attention for these. They're all gases, and that's going to be an important part of this. And it wants you to figure out the delta H for that reaction. So what you have to do is go to your reference packet and go to the heats of reactions page. And what you want to do is pick out those 4 things. So what you do is find them on the left-hand side. And if they show up on the left-hand side, we're going to have to make a note of that. So one of them was NH3, which is right here. All right, so I'm going to end up copying that down on the other page. Now the next thing listed was O2. Oxygen gas, if you notice, doesn't show up anywhere on this page in the left-hand column. All right, so that means you skip it. The next thing listed was nitrogen monoxide, which is right here. and then you have 6 moles of water. And I said to pay attention because it is steam. It's in the gaseous state. So we need to pay attention to this water. So what I did is I just copied them over to this page so we can kind of work on it here instead of going back and forth. Now I said there's a shortcut you could do with this. If you're going to do the shortcut for this, what you end up doing is delta H equals the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. Because remember, when you do delta H or delta anything, it's always final minus initial. So for chemical reaction, final are the products, initial are the reactants. Now, when you're doing it this way, if you do the shortcut method, you have to pay attention to the coefficients. So what we are going to do to figure out delta H is we are going to add up all of the enthalpies of the products. So the first product is for nitrogen monoxide. So we find the nitrogen monoxide and we write down the delta H. Now the good thing, or one of the things you have to remember if you do the shortcut method, is you never change the signs for the delta H. If it's listed as negative, write it as negative. If it's listed as positive, write it as positive. I don't care if it's showing up as a product or a reactant. The fact that we do products minus reactants takes those negatives and positives into account. So you just leave them exactly how they are. So what we have to do is do 4 times the delta H for nitrogen monoxide, which is 90.4. Add to it the other product, which is 6 moles of steam. So we're going to do 6 times the number for steam, which is negative 242.0. That takes care of the 2 products. Now, on the reactant side, nothing was listed for O2 in that left-hand column. So we left O2 out of it. What you see is O2 shows up kind of all over the place here. So it's just going to work itself out in the end. So the only reactant we have to work with is 4 moles of ammonia. So we subtract out the reactants. There's only one reactant to work with. We do 4 times the delta H for ammonia, which is negative 46.0. Now, paying attention to the order of operations, what you should get as the delta H overall is negative 906.4 kilojoules. Now, if it helps, what you can always do is write out the answers to each of these steps. So 4 times 90.4 gives you 361.6. What you end up doing is adding that to 6 times negative 242, which that gives you a negative 1452. All right, that is the product side. And then, well, you're basically going to subtract out 4 times negative 46, so that will be a positive. So it's like adding 1 in, oh, that'll be the 0. Okay, so pay attention to the order of operations. When you do the shortcut method, you never change the signs for the delta H's. Just write them down exactly how they are. Make sure you do products minus reactants.